Okay, good morning. Um, we're continuing on with our image quality lecture. And I think where we left last time, we were looking at a detection task, which was sort of at the threshold of the signal to noise that we ever use in imaging. In fact, this is well below the signal to noise threshold that you would use to detect something in medical imaging. The interesting thing about this pattern for you to notice is that this is what's called white noise. Right? The background here has absolutely all frequencies possibly that you can depict with this 256 squared matrix represented. And that is, they're totally random numbers, right, that are coming up in a random sequence. And so the statistics on this field, except for that thing that's crossing the field along the diagonal, the statistics is the same everywhere. It's a Gaussian noise field, and if you looked at a single pixel and you looked at how the signal intensity of that single pixel is changing with time, and you take that root mean square deviation, it's the same as if you take a single time frame and put a box around an area and take the root mean square deviation in there. That's called an ergodic and stationary system. And it basically, the noise in time and the noise in space is the same. This is ideal noise, actually, for doing any kind of detection task or statistics or anything like that. You have a Gaussian distribution of random values, and you're going to try and see or detect a signal inside that noise pattern. Right? So it doesn't have the noise itself doesn't have any structure. Here, you can see that thing gliding across diagonally, probably because your eye is averaging the signal over that area, and you're seeing a different statistic in that box. I thought it was because of the motion, but one of the students last year said, well, I don't think it's because of the motion. I think it's just because you're averaging, right? And I said, oh, no, watch. If we put it in one place, you won't be able to see it. And of course, we put it in one place, and you can still see it, right? So it is principally because you're averaging, right, with your eye in time, that you get a different statistic at that location. You can still see that thing. It's not as evident. It's not as fun, right? But you can still see it. So, and this is what it looks like when you freeze time, and you have one instance of that object. Now that your eye is kind of trained to look for it, it can kind of see it, right? I mean, if you were to say, where is it? You'd probably look at a point right here and say, yeah, the statistics right in here looks a little different, right? But now you're trained to look for that. Right? Before, you wouldn't have been able to see that. And if you look at the statistics quantitatively, it's pretty darn subtle, right? In one dimension, you wouldn't pull out this region and say, oh, that region's different, right? So there's something going on not only in your training to look for that signal, but you also have trained yourself to average over that dimension. Because when you break it down to a lower dimension, you can't see the signal, really. You're not going to detect it. So these detection tasks are, people have studied human detection for simple tasks quite extensively, and to some extent it has implications for radiology and cardiology in the sense that you're looking for things in images, and so you'd like to know the threshold of detection. But human beings, specifically physicians who are making a call for a specific patient, don't like to work down in the area that is an interesting area to study in terms of perception and detection. They don't like working down there at all, right? They like to work way up in the space where the detection task is much more simple and much more direct, right? So it's our job to make pictures that are just better than down here. Now, you eventually have to make a decision in, say, X-ray imaging. You can make better and better pictures by using more and more X-rays. But if you use more and more X-rays, the dose to the patient gets higher, And so you have to find some trade-off, usually, right? Specifically, if you're using ionizing radiation like X-rays to image children, right, they're more susceptible to radiation damage and the consequences of that because they have much longer to live, right, from the time you're radiating them. If it's an 87-year-old man who you're looking and deciding, do I put an aortic valve in this person? Radiation isn't a huge issue there because the time it takes for cancer and everything to develop is much longer than that person's going to live their natural life. So that's not a big issue. So here's an example of signal to noise, or image quality as depicted by signal to noise, for a specific image at two different X-ray dosage levels, or two different intensities of X-rays used to make this picture. So this image here, the X-ray tube was set such that 700 milliamps of current of the electron beam was hitting the target to make the X-rays. Then you turn that current down to 1/10 of that value. So now you have 1/10 of the X-rays making the picture, and you get this picture. Right? So this one's much better. Just by looking at it, you say, I like this picture better. This one has a lot more of the random signal values in areas that are supposed to be constant. And one of the things that's subtly different is that the edges in this one are slightly blurred. And that's due to CT image reconstruction. They customize image reconstruction to make more averaging if you don't have enough photons, and they do it by blurring a little bit. If you take the difference between this picture and this picture, there are differences in, say, the mean value of the blood signal here. That could be 600 Hounsfield units in this picture on average and 600 on this picture. It's just noisier over here. So when you take the difference, you see that there's a zero mean, right? There isn't a difference there. But what you're looking at is the noise field. This noise is independent from this noise. And so you're basically imaging the noise field here. And some features that are different due to the lower X-ray count. Particularly if you look at certain really sharp features or high edge, high frequency features, say down here in this picture, but this versus this, you see a noise field from the difference of the two pictures with a different number of photons, but also there's a very bright difference at the edge of this structure. Right? So if we zoom into that, let's just zoom in there and take a look. This is at 700 MA. This is 1/10 of the photons. You can see that you depict the edge of that structure much better than you do here. Right? In fact, here it's questionable whether you would call that a structure. Did anybody have a guess what this structure is? If we go back to the original picture, this is the aorta, all right? And coming off the aorta, remember the right coronary artery will come out here. The left main comes off here. All right, so anybody have a guess what that structure is? It was one of the treatments that we looked at 2 lectures ago. And you put it in with a balloon and you blow it up. Right? It's a stent. Right? So metallic stents come up really bright in CT, right? Because metal stops X-rays very well, right? Whereas soft tissue doesn't stop it as well. So if we're looking at what do we do with these pictures, the image quality in this picture is probably sufficient to answer the question, what's the volume of blood in the left ventricle? Right? You're probably going to get a reasonably good estimate for that. Right? If, on the other hand, your job is to determine, is there signal in the left anterior descending coronary artery at this location, and is that signal bright, then this image is not going to do that for you. You're not going to make that call with this image. If you do, you're just asking for trouble, right? Because you're going to make the wrong call. So for those two tasks, the image quality in one case is sufficient in this picture, and in the other case it is not. So it really is tied to what you want to do with the picture, right? What your image quality has to be. And so what we're going to do for part of the homework, and you can just hack around on your own, is we'll look at some medical images with two pieces of software. They're both free, and you can download both of them. So those of you that have a Mac computer, you can download software called Horos, and everybody can download software called ImageJ. And we'll put instructions on how to do that. So if you have a PC, ImageJ is fine. Everything we want to do with the images in terms of analyzing the structure of the signal in the images, we can do with ImageJ, so it's not a big deal. This is a nice piece of software if you want to read in DICOM pictures. So any imaging device, whether it be an X-ray angiogram machine, an ultrasound machine, nuclear medicine, MR and CT, they all write out DICOM files, which is this medical imaging standard now, and Horos will read those DICOM files and actually read the headers and put the correct scaling and everything together and sort the images most of the time. ImageJ does a reasonable job at that, but it basically it assumes just that you sequence the pictures correctly and you read them in, and then the sequence will be correct, etc. Who's played around with Photoshop or some other, or GIMP or some program like that you do imaging analysis with? Nobody? Really? So you just take the pictures that come out of your camera and run with them. Oh, you're crazy, man. Like, you should download a program called GIMP. It's called GIMP. You can change the pictures such that they look much better. My wife and I have a picture of us, and we're walking outside the Colosseum, right, in Rome. Beautiful picture. The lighting's perfect. Remarkably, both of us are looking okay. And then behind us is three huge British tourists, like sitting from like this. You can just eliminate them from that picture. It's like, boop, 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 they're gone. And now it's just the Colosseum, right? I'll show you that picture one day. So those things, you can just take a part of a picture, paste it, make things. It's dangerous in medical imaging, as you can imagine, right? So people have been caught modifying images, saying, I think we could increase the contrast here a little bit. And it's not money. People don't, usually in academia, people don't do egregious things out of money. It's usually not the reason. It's usually because they really want to be, top in their field, remarkably, right? And so their technique, they think, there's a reason why that looks like that. It should look like this, and we'll just change it. And but how do you think you can catch images that aren't legit? Just, if you're looking at an image and something looks weird, what is it usually that looks weird? It's the noise, right? So you're looking at it, you say, that shouldn't happen, right? This signal is just too good, right? And then when you go back and you look at the actual noise statistics, you say, yep, that did not happen, right? Something else came in here and made signal. So, but now we're in an era, a whole new era of image analysis and image forgery, because you can basically train a neural net on 300 Rembrandt paintings, and then say, make a Rembrandt of this guy, and boof, it'll make a portrait that looks like a Rembrandt, right? And really hard to detect, right? Because it'll get all of the background noise and all that stuff right. So it goes the other way. We won't do AI in this course, but it's medical imaging and AI are becoming absolutely entangled and in mysterious ways. Okay, so we're going to use ImageJ. You'll be able to do everything we ask in your problem set with ImageJ. And we'll do some examples at the end of this lecture. where are we going here? Oh, okay. So signal to noise, contrast to noise, they're simple scalar numbers, so they're very convenient, right? If I have image 1 and the signal to noise is 10, and image 2 and the signal to noise is 5, I know that image 1 is quote-unquote better, okay? And I've spent time improving my imaging to get to that signal to noise of 10. But they don't answer the detection question. And so to do that, you use metrics called sensitivity and specificity. And this is used in all signal processing, sensitivity, specificity. And basically, sensitivity is your ability to extract cases that are positive, right, from the pool of cases. So I have a whole pool of cases, and there's some fraction, say 20 people out of 100 are positive. What is my ability to extract those 20? Do I get all 20? If you get all 20, your sensitivity is high. Okay? And specificity is the ability to, while extracting those positive cases, eliminate the negative cases. Okay? So you want basically to extract the true negatives with the same fidelity out of that signal. So if you call everybody positive in that 100, your sensitivity is 100%, but your specificity is very low. Right? So another very useful thing to calculate when you're evaluating images is the positive predictive value and the negative predictive value of the calls that you've made using those pictures. And these are very useful when you have tremendous imbalances in the number of people that are negative versus the number of people who are positive in your cohort. So if I have 1,000 patients and 10 of them, right, have the disease that I'm looking for, right? My sort of specificity is great if I just call everybody positive. And it doesn't look that bad because I only missed 10 out of 1,000, right? So your sensitivity you've sacrificed to just say, you know, I never make a wrong call. I make a wrong call 10 out of 1,000 times, which is a pretty good number, right? So what you need to do is like get a metric where you look at the true positives that you call divided by all of the true positives and all of the false positives. And that's called the positive predictive value. And that tells you the fraction of people who are positive whom you call positive. Okay, so think of it this way. If I have a test, 1,000 people come through, and I call 100 people positive, I put those 100 people in a room. Okay, everybody's been called positive. And now you ask the question, how many people, what fraction of people in that room are positive? That's the positive predictive value. Okay? And if 90 of the 100 are positive, then that's a very good positive predictive value. We'll see, you know, sometimes it's 50%, right? And the issue is whether or not calling somebody positive leads to bad things downstream. There's a risk in being called positive, i.e. you get a biopsy, you go to the cath lab, you have some procedure that you didn't need, and you really want that positive predictive value to be high. And as we talked before, that in cardiac CT, it has a remarkable negative predictive value. That is, if you have a CT scan for coronary artery disease, and when they read the scan, it looks like you have clear vessels with no lesions in them. The negative predictive value, if you get called negative, is about 99% for CT. Very rarely do people get called positive who have a negative value or a negative scan. Okay? It's hard to basically make by accident a really good looking coronary vessel on an image, right? There's not many artifacts that make the vessel look better, right? artifacts make the vessel look worse. They make it look like it's positive. We looked at these definitions, so we'll click through those. But another common thing you'll see in publications that are evaluating an imaging diagnostic test is this 2x2 confusion matrix. And you have a group of truly positive patients and a group of negative patients, and you're trying to separate them, and you get these 4 categories of results, right? And the 2 categories that are good are the true negatives, and so your observer, like using the images, calls the person normal, i.e. they don't have the disease, so they're negative, and they actually are normal. That's true negative. And then true positive is another good result, right? Where the person has the disease and you've actually detected the disease and you call them positive, and those are the true positives. So if we had 100 people, 50 with the disease and 50 don't have the disease, the ideal result for this matrix would be 50 in this box, 50 in this box, right? And that would be a perfect test. That does not happen ever, in medicine. So what happens is you basically call, the observer looks at the picture, says, you know what, I don't think this person has the disease, calls them negative, but they actually do have the disease. Right? That's a false negative call. And then the opposite is you call them positive, but they're normal. Right? And so if all of these are, say there's 25 in each box, then you wonder about your test, right? That's sort of a random result. If I had 100 people and I put 25 in each one of these boxes, then I may as well just be flipping coins to sort people into the boxes, right? So you really do need to have folks wind up in these 2 boxes to have a reasonable test. Using these boxes, you can calculate your false positive rate and your sensitivity and the specificity and the positive predictive value. So let's remember these: true negative, false positive, true positive. Those are the definition. And we're going to define sensitivity and specificity in terms of those fractions in that confusion matrix. Okay? And it also relates to the area under the distribution of patients of that type. So if in my cohort that comes through my clinic, I add up my number of cases at each one of these values of a decision parameter. So let's say my decision parameter is brightness of a lesion, right, in a liver, or another decision parameter could be the diameter of a coronary vessel as seen on CT, right? So that's just a number. I compute it and I say below a certain diameter, I'm going to call that person positive. Another way of looking at that is to say if the percentage stenosis is high enough, I will call that person positive. So let's call it that. So let's say this is percentage stenosis. So what we're going to say is above a 50% percentage stenosis, we will call people positive for coronary disease. Here's all of my normals, and they have a distribution of percentage stenosis that looks like that, right? And so then you say, well, what do you mean by normal? You need a gold standard to say that person's normal, and oftentimes that gold standard is coronary angiography, so X-ray angiography. So this distribution here shows the distribution of percentage stenosis in people who have a negative cath. Therefore, they're normal, right? And this is the distribution of stenosis measured in the cath lab for people that have a positive cath. Those of you who are on top of things say, why would you ever call these people positive with such a small stenosis? But let's forget about that for the time. So these are the folks who get called positive or abnormal. We're going to set our threshold, T, at 50. Okay? Now, our basically true positive fraction is this area here, divided by the whole area of the positives. Okay, so that's the true positive fraction, this integral under here. And the false negative fraction is this area under here, this tail here. Because these folks are positive and I've called them negative. They're on the wrong side of our threshold, right? The false positive fraction are all the normal people that are above the threshold, so it's this area under the curve. And then the true normals are the folks that luckily are under the threshold here. Okay? So remember the example we had of that, the ultrasound clinic that was looking at those stress tests, and we got ridiculously different rates of calling people positive? And that's because the behavior of those physicians that made that call is different. So the observers are different. So how do you take the observer out of the mess? The way you take the observer out is you adjust this threshold and see how you do as the threshold moves. So if I put the threshold up here, right, that would mean I'm a more, say, conservative observer in the sense that I really need to see a high stenosis rate, say above 70, before I call somebody positive, right? So I only send this group above 70, this number of people. But I miss a whole bunch of positives. You can be a very aggressive reader, and that is every time you see something that just has a hint that it could be positive, you call it positive. Your threshold as an aggressive reader is down here. So you're calling all of these people positive. You catch almost everybody in the positive cohort, but you also catch a lot of normals. As you move this threshold from high down to low, you can draw out the true positive fraction that you catch versus the false positive fraction that you catch. Okay? If our threshold is very low, if I put it down here and call everybody positive, then I wind up at this point on this curve. I get 100% true positive fraction. Everybody who was positive got called positive. But I also get a huge false positive fraction. 100% of the people who are negative got called positive. So we're up in this top right corner. This is where we do not want to be, right? In fact, we don't want to be anywhere. You can't really be below the line unless you really try. But if you flip a coin, you get anywhere on this line, right? So here, 50-50, is just flipping a coin. What we really want to be is over here. We'd like to be at 0.9 and say 0.1, where we get 90% of the true positive fraction is our call. Pick up 90% of the positives while only including 10% of the people who are negative. So what this does is by scanning T across your sample, you basically draw a line in this space. Okay, so eventually when we're way up here, we don't call anybody positive, and so we're at 0, 0. And it's this line, it's called the receiver operator characteristic curve, or the ROC curve, that defines the ability of the technique to take those two distributions and pull them apart into their correct categories. Right? So you've taken the observer out of that evaluation. You basically, test different thresholds and look at this curve and see how close this curve gets to that corner. And you'll see this curve often in papers where people are evaluating, say, CT for the detection of a coronary disease versus nuclear medicine, right? They might, have an ROC curve for the CT and ROC curve for the nuclear medicine. The one issue that occurs when you just use ROC curves is if there's a tremendous imbalance in these two distributions in terms of the number of cases that are there, right? So if I only have 20 of these and I have 2,000 normals, then drawing this RC curve gets you a result that is a little weird in the sense that you can have high true positive fraction, right? You can detect a lot of people, and your fraction of false positives is still pretty small, even though the absolute number is really high, right, compared to the number of true positives. And so that's an imbalance issue between the two distributions, and oftentimes people will use a precision recall curve to try and alleviate that problem when you have these imbalances. But the RC curve is fine if you've got, especially if you've got 50-50 and you're looking for the ability to take those apart. The positive predictive value is sometimes called the precision in a precision recall, and it will tell you if you have a problem when you have this big imbalance. So the positive predictive value, remember we did the example, is the number of true positives in the room divided by the whole number of people that got positive. So we put everybody in a room that's positive, that got called positive, and we figure out who's true positive. That fraction is the positive predictive value. Okay? And so that is often used. And if you're reviewing a paper and people put up an ROC curve, you should be wary, right? And compute these numbers, or ask them to compute the numbers if they haven't, because it often reveals a better estimate of the performance. Okay, so in CT, for example, the positive predictive value of true coronary disease when you give CT scans to a novice reader, somebody who hasn't read a ton of them, and you say, you pull out the positives, the positive predictive value of novice readers in cardiac CT is about 50%. That is, they call just as many negative people positive as they call positive people. And that's a problem, right? So when those people go to the cath lab, cardiologist shoots the dye and says, there's no lesion here. The person who called them positive, gets to know about it. They get a phone call and say, why are you doing that? Why are you sending us positive people? Right? Or negative scans. I mean, these people don't have disease. Whereas the negative predictive value of CT is super high. It's 99%. So you very rarely send people who have clear CT scans to the cath lab. And, you're accurate on that end. Which is good for screening. If you have chest pain, you go in. If your vessels are open, 99% chance you do not have coronary disease, so you can go home. Okay, so what I'm going to do for a little while is we're going to look at how to analyze images in ImageJ. We'll just take a look at some example medical images. These we're going to upload onto the website a set of images for your problem set, and you'll be asked to measure certain characteristics like what's the signal to noise, are the edges blurry, if you do this type of averaging to improve the noise, what does that do to the spatial resolution, etc. But before we get into that, any questions about any of this stuff we just talked about? Yep.
So like those novices reading the CT scans, who would that be in a hospital? Would it be like a new radiologist, or would it just be like an intern?
It would be can be a number of people. A fellow who's doing non-invasive cardiac imaging as a fellowship, right? And so they come in, and usually residents and fellows start on July 1st in hospitals. So if you go to an academic medical center, don't go in July, right? Because that's when all the new fellows and residents are there, and they're all just figuring out what the heck's going on. You kind of want to wait 6 months and show up, in the winter. And everybody, after Christmas, like New Year's, after everybody gets back, everybody's like going in full mode, right? So then the other thing is, if it's a new modality in a hospital, then the attendings have to figure out how to read this new modality. Usually you go to a CME, continuing medical education course, in which in that course they will force you to read, say, 500 cases. And then you at least have a 500 case training set that you've got. And humans are the best AI machines known. I mean, it really, training on these deep learning algorithms takes a lot of data. Training on humans takes a case of one. They look at it, they get burned once, and they remember, right? And so they'll never do that again, right? Especially if it led to something really bad, right? And so humans make their way through training very rapidly and become really good really fast at recognizing disease and stuff like that. Any other questions? That's why big data, to me, I mean, big data is okay and all if you're doing something like, I don't know, predicting if somebody's going to default on their credit card or something, I guess. But for medicine, big data has an interesting twist in that each person, each case is really kind of unique. And it's the uniqueness of the case which often is the super training element of it. And so medical education, if you sit and with residents and fellows, medical education is done on an individual case-by-case basis and like, don't let this happen to you, kind of thing. Don't prescribe this drug with this drug. Bad things happen. Don't do that. And so until they see the consequences or feel the consequences of it, once they do, they'll never do it again, right? And it's sort of all of the senior faculty, they're chiming in on each case on what you don't do at this point and stuff like that. Yeah?
You mentioned that there's not many artifacts that make like a vessel appear better. What would be an example of one that
might make a vessel appear better?
Yeah.
Okay, so that's a great question. So the question is, on negative CTA, you have open vessels. And so the diameter of the vessels looks uniform and they look bright. Okay, as we page through the data, we get uniform, open, bright vessels. What artifact could make a closed or a smaller vessel look like an open vessel? Okay, so actually, there's one sort of common sense type of thing. If I have a small thing on an image, how do I make it bigger? There's two ways probably. One is it moves during the acquisition, right? So it can, if I have a circle of this diameter and it moves across its full diameter during the acquisition, and I get remarkably some beautiful scan that just shows a larger object, then I've missed the fact that it's actually a small thing, right? The other is that if my resolution isn't high enough and a small thing looks like a bigger thing because it's blurred, right? Then I look and say, no, I don't think that vessel is that small. But in fact, the image has blurred for whatever reason. And the blurring can occur because maybe it's a big person and the number of X-rays detected was low, and so that the reconstruction accommodated for this higher noise level by smoothing. And so it smooths everything, and so the vessels got bigger. Luckily, when that occurs, clinicians usually can detect that, and they won't call, the person normal. The other thing is that just the brightness of the vessel in an abnormal region, it gets dimmer. And so when you're paging through the scan, you go, whoa, what's that? And you just page back and forth and say, oh, it got dimmer. Even if it doesn't change its dimension, if it gets dimmer, there's less contrast in there, and therefore it's probably a smaller vessel. The problem for calling too many people positive on something like CT is the fact that you have, in many people that are older, coronary calcium. And calcium is a super bright signal on CT, and so it really interferes with the underlying vessel signal. So you have this huge bright signal, and you're trying to look in the heel of this bright signal what's going on, and that gets confusing. And so the safest thing to do at that point is just say, it's probably positive, send the person to cath, right? Okay, those are good questions. All right, so I'm going to sit down and introduce you to a couple of pieces of software here. And I'm sorry the problem set isn't up yet. I got really busy yesterday. My daughter got sick, so we will have on the website by this evening the problem set and some example data sets and the lecture and all that kind of stuff. Okay, let's go here. Okay, so for those of you who have a Macintosh computer, unfortunately this software only works on a Mac, but it's free, and it's a really nice piece of software other than the fact that it keeps reminding you to update it. And so, for example, this is an MR data set. You can, if it's any kind of bag of DICOM files, it doesn't really matter what folder structure they have or anything. You just drag the thing into Horos, and it will pull out different types of images, different series for you. And so, for example, here's one. There's 270 images in this thing. So we can then click, say, 4D viewer. It should sort those images into space and time. So here's space. So if I click the left arrow, I can click through different slices. These are short axis slices of the heart. And then the up-down arrow will give me different time frames, right? And so if you just hold your hand on the down arrow, you get a movie, right? Now hold your finger on the down arrow. It's wasn't designed to do this, but computers are fast enough now to do this, right? So here you can look and see, cardiac function in the middle of the ventricle. Now we click down to the apex. There's function at the apex, down at the bottom, and click back up to the valve plane. Here's what the valve plane looks like. This is the aortic valve here. This is the top of the left ventricle, so it's just inside the mitral valve. And then there's just the base of the left ventricle here. If you want, once you have the DICOM files and everything set up, you can then extract things. So if I'm on this slice and I say Command on a Mac, Command E, it will bring up the ability to extract those pictures into their own series, and then you can export it as to whatever you want, right? So here we do axial. We'll call this series Axial Movie 2. We'll say it's the fourth dimension. So current image, it would just extract that picture. Fourth dimension, it's going to take that slice and extract all the time frames of that slice. Right? So, just in terms of image management for space and time, this is a nice piece of software to have if you have the ability to download it. So you say OK, and it will extract into, so here it is here, Axial Movie 2 is now 30 images, and they're different time frames, right, in a single slice. So if I double click on that, bring it up, I now have only 30 images, and it's those time frames, right? There are some analysis tools in here. For example, I can make an oval and measure, say, the mean image intensity and the standard deviation of the signal, and basic statistics like that. What else is useful here? Oh, basically center and window. So if you want a threshold to determine whether or not you can adequately threshold something, here I have basically by changing the window level to 2, that means everything above this signal value of 776 goes to white, and everything below 774 goes to black. And so you've now got a binary picture. So if you wanted to compute, say, what is the amount of blood in this slice, you could make a binary decision as to what is blood and what is not by changing this threshold. So if I'm at 776 and I move up and down, let's open it up a bit. So I move up and down, you can see the border of the ventricle changes a little bit, and I start losing pixels inside the blood volume as I go up to 1,070. If I set my threshold even higher, then I start losing a lot of pixels inside the blood pool. If we go back down, and all I'm going to do is count up these pixels, and that's going to, and the volume of each voxel, when I count all that up, that gives me the volume of blood in that slice. But I have to, if I keep going up, you can see it gets bigger and bigger and bigger as the sides, expand slightly, right? So deciding where you're going to set this threshold above which you will call something blood is part of image segmentation, right? Just like, how do I segment this picture into blood and everything else? And blood is both spatially, it's inside the ventricle here, and it's above a certain signal level. And we'll call that blood. Out here, there's stuff that is above that signal level. It's also selected. It's fat. We don't want that. So we need the spatial part of it as well. Okay. Okay. So once we have sorted things out and we have Axial Movie 2 here, we can then export Axial Movie 2 and MRI Stags. Okay, so we just made a new folder of Axial Movie 2. So it puts it in a folder, and then this is going to write DICOM files into that folder, right? And it'll be that set of DICOM files. Right now, they only exist inside the software, these images, but what I just did was I put them out in a folder on my disk drive, so now we can manipulate them with other software programs. So if we come out and start up, this is called ImageJ, and we'll look at what we've got here. Let's start fresh here. I think I probably put it here. Okay, so we put our images in here. And so they're a set of now DICOM files. And they have, the DICOM file has a header and telling those programs that can read it what the spatial dimension is of the voxels, what the orientation is of the slice, etc. Each file looks like it's about 1/4 megabyte, 224 kilobytes of data. These files are 16 bits, more than likely. So what we can do at that point is take the whole group of them. Well, let's do this first. We can take one file, one DICOM file, drag it in here, and it opens. And it has the proper format, 192 by 256, and it claims it's 16 bits. Okay, so there's our picture, and that's now inside ImageJ. Okay, so we can now manipulate this image inside ImageJ. So let's start looking at what we could do. We can make an ellipse, say like so. And so all of the pixels inside that ellipse will take a look at their value. So, online you'll find a manual for ImageJ, and we can have also a tutorial section where we look at particular features that will be useful for solving problems on the problem set, for example. But one thing we'd like to know is what does the signal look like of all of these pixels? And if we go in here, process, analyze, so you see this, it does a whole bunch of things. But let's look at a histogram. It's very useful. So here's the value of a pixel in terms of its brightness. Between 518 and 1479 is the range of values it found inside here. Obviously, these dark things here are likely this signal down here, and the blood is this Gaussian distribution of signal up here, right? Sort of. And you know, if I come along here and I say, well, what is the mean of that? It's about 13. If I look in the bottom corner down here, that tells me, I think, does that tell me? Yeah, 1479. So it's about 1340 is probably the mean of the blood signal, right? If we wanted to extract all of the blood, we might think about putting our cutoff here at 1100, maybe, and say, okay, everything above here we're going to call blood. All that stuff is this other tissue. Let's look at the histogram. We'll kill this of the whole heart. So now we're going to look at signal values that have blood and myocardium. Right? Let's analyze histogram. Okay, so now we have two groups of pixel values, two classes of pixels. This, the low one, down here at about 380, and this, again, up about 1300. Blood, myocardium. Right? So if you wanted to separate the blood and the myocardium, and you were going to put a quantitative T decision boundary between those two signals, where would you put it? Anybody want to guess where you'd put it? So anything above the threshold, anything below the threshold. So above the threshold we'll call blood, below the threshold we'll call muscle. So put it right in the middle, maybe. That's a guess. Right? Or if it's more important to call everything blood that's blood, and there's a penalty for calling something blood that isn't blood, you may want to roll it up a bit right to the side of this distribution. If these guys are misclassified as blood and they cause you trouble for being so, then you want to eliminate them, right? Vice versa, if you want to include dim blood, you know, that's on the boundaries, then you go down here. But the center looks like a reasonable spot. And then you could just set that, and at least it's a quantitative decision boundary that if everybody segments the data, we're all going to get the same answer, right? So that's one way to set a decision boundary or for segmentation, right? We can also look at the spatial characteristics of the image by drawing a line through an object that's of interest to us, say the heart, oops, my bad, here, and pop up a profile here. Okay, so this, if I look at pixels along here, I sample pixels along this line, I see that I start down here at a very low signal value in the lung, right? I get some complex structure right here, it's here, and then it pops up to a signal value here. Remember, blood was 1300, so it's 11, 12, 13, so it's in here somewhere. This is the blood signal. This divot here would be that signal there, which is a papillary muscle that's sitting in the ventricle. So it's a little piece of muscle reaching up to the mitral valve, and it has dark signal. The cool thing about this, you can say live and move this around to look at different structures. So here, this is a better depiction of just isolating blood from background, myocardium back here. So this would be the myocardium, this would be myocardium, and this would be blood. Right? If we want to look at the sharpness of the edge in the image, then we can take a look at an edge as depicted in our image like that. Right? So we have blood on this side, that's this signal, which is in the right ventricle. And then as we move into the myocardium, the signal goes down. Let's bring it up so you can see that. Remember, blood's around 12, 1300. Myocardium was down, I guess, around 375 down here. And then it rolls back up to the blood inside the left ventricle. So this kind of gives you an idea of what spatial resolution we're looking at, right? Because the slope of this line, if this is truly a discrete surface, and ideally it would be a hard edge between the blood and the myocardium, whatever we've done making the image has changed that to this, signal that has a slope, right? And in deciding where the blood starts and where the myocardium stops, you have to decide where up this slope you're going to make that call. And so it could be here. You say anything above 1100, I'm going to call all of this stuff blood, and then I'll call everything else myocardium. Well, all of this signal here is sort of a partial myocardium, partial blood, because myocardium is down here, right? And a lot of this occurs because of lack of spatial resolution. And so if I have a large voxel, right, inside that voxel I can have some blood and some myocardium, right? And then that will blur my signal. In MR, the slice thickness here is probably about 7 millimeters. So it's a fairly thick slice, and so the signal is a little blurry on the side. But again, depends what you want to do. If what you want to calculate is how much blood volume is in this slice, it's perfectly fine. This resolution is probably going to make that calculation very, very well. If, on the other hand, what you want to calculate is how far does this edge move in 30 milliseconds. So your ability to detect where that edge is obviously dependent on what this slope is, right? If the slope's really hard, then you can see it move back and forth. If it's, got something like this, you have to fit the whole damn object as it's moving back and forth, right? So depends what you want to do. Okay, so let's kill that. Kill that. Some other very useful phenomenon here. So you can take the whole stack of 30 images and pick them up, drag them in, and it puts them all in there. So now you've got 30 independent fields that you can work with. But one of the great things about this software is you can take those 30 pictures and put them images to stack. So you can stack all those inside one data structure, right? And so if we do that, we call this stack one. It takes all of those and puts them into one stack. Okay? And now you can go back and forth temporally, right? Oh, let's zoom that up. So as we move through the stack, we get the different time frames, right? So in terms of cardiac function, how much the muscle is contracting, one of the things you might like to measure is what's the dimension of this structure as a function of time, right? And so that would be the wall thickening, a radial wall thickening. If we look at this image, we see we have a problem, right? As it contracts, it looks like that wall might get a little bit thicker, but right here, something else is going on. Does anybody know what's going on there? Can you determine? Like, it's not getting thicker. It turns out that the heart itself is moving through this imaging plane. It's not staying at one level. It's actually a three-dimensional object that is moving through space, right? And so as the heart contracts, this tissue that we see here, by the time we get to here, that tissue is long gone. It's actually about 2 centimeters into the page, right? Or maybe 1 centimeter into the page. And so you've now got different tissue that you're sampling as it's going through. So let's actually go back to Horos, and we'll find some tissue that's easier to track. Okay. These are long axis views of the heart. Let's read those into time and space. Okay, so these are different time frames, right? Looking at the heart from an orthogonal direction from the one that we were just looking at. And then these are different long axis views of the heart. It's interesting to note also, with MR, you can determine somebody's percentage body fat very, very well, right? Because this white signal here is fat, all this stuff. This is blood, but all this business here is fat. And so it's actually not that difficult to separate out all the fat and all the other tissue. And so with MR, you get a really nice estimate of what the body fat is. So let's, would this be a good one? Yeah, okay, let's use this one. So what we're going to do is we'll figure out what the performance of this wall of the heart. Has anybody looked at their anatomy picture of the heart, and can anybody tell me what that wall is? Each wall has a name, remember? This is called the septum because it's between the right ventricle and the left ventricle. It divides the two chambers, here to here. Sometimes people have a small hole in their septum called a septal, what is it called? I forgot. But anyway, and so under normal conditions, we start with a certain thickness of the septum, and then as the heart contracts, it gets thicker, right, to there. And that is a hallmark of good cardiac function, is the thickness, right? So let's take this slice and save it. So we'll go Command E, fourth dimension, LAX, septum movie 1. Long axis is what these views are versus a short axis, which is that donut view, and it includes the septum. Okay, so that looks good. And if we go back to our essentially database here, LAX septum movie 1 is here. Okay, just open that. Those are our pictures. It's pretty nice, right? And when everything goes well in MR, it's just fantastic. It's a beautiful depiction of how the heart's moving. These are vessels right here, coronary vessels lighting up. You know, as the heart contracts, see how it gets brighter because blood is like squishing through that vessel. And the vessel is embedded in a pad of fat, which is really nicely depicted here in the MR. So it's really nice. So let's then take that LA septum movie. We're going to export it into pictures. We'll go up. Create that and export those files. Okay. Let's go back to our Finder. Okay, here's our new data. It makes a nice structure for it. So we've got 30 time frames from 1 down to 30. Okay, and let's go into ImageJ and collect up those pictures. Stick them in there. All right. Let's make a stack. Images to stack. Okay. Now, inside ImageJ, we can start making those measurements. Let's get a line. We'll put it through the septum, right? So it's centered up on the septum, and we can now do a profile here. All right, we might have to make this a little smaller, actually. Smaller. Okay. So if we go live, we should be able to. Oh, I broke it. Okay. That's no good. Let's see. Let's go back to this. See if it comes back to life. Yeah, it's not doing that. Tell you what, let's read them in again. Okay. Image, we'll make a stack. Okay. Let's put that line across there like so. And where it was analyzed, right, is plot profile. There we go. Okay. So as we move from the right ventricle blood here at 1300 down, here's the myocardium at 375 or something. It goes back up to the left ventricular blood. So this is the wall thickness, right, of the myocardium there. I think if I go live, I should be able, yeah. Okay, so as the heart contracts, there we're sort of at where the atria are maximally full of blood and the ventricle is maximally emptied. We now have a new thickness along here, right? And so you could measure, again, you have to decide, okay, how do I measure this thickness? Where do I put my point to measure from here to here, right? And so to make it a quantitative thing, you need to make these decisions. And then we can move it around, say look at more orthogonal view here, and right, it goes back to its original thinner condition. Right, so that's myocardial thickening. You can measure that with this quite easily. Now, again, the trick comes in, what do you call the position across here that you're going to measure? How do you determine that? Is it the half height? Is it the height between the blood signals, et cetera, right? What else can we look at? Oh, I know what we can do. Let's measure the signal to noise. So if I take one of these pictures, right? Let's take this one and drag it in. And we blow this up and ask the question, what is the contrast to noise between the blood and the myocardium? Right? So we need basically 4 things to make that measurement. One is the signal intensity of the blood, 1, signal intensity of the myocardium, 2, and then the noise on the blood and the noise on the myocardium. In magnetic resonance, when we're looking at these pictures, the noise really, it's spatially dependent because, you know, as you approach the receiver coil, the signal to noise just goes up, right? So as I move away from the center of the image where all of the voxels are as far as they can be from a receiver coil, and I move up towards the receiver coil, the signal to noise gets better and better and better as I get towards the receiver coil. And so this is kind of the worst place. It's hard to visualize that with this picture, right? Like, what is the signal to noise as a function of position in this picture? It's not that easy to visualize. So one way to do it is to find a couple of images that are close together in terms of their shape, right, and just subtract them. And what should be left? If it's the same shape and you subtract them, the thing that is left is an estimate of the noise, if the noise on those two pictures is independent. And in MR, that's a good bet, is that for 2 time frames, the noise is independent. Sometimes they interpolate across time, most of the time not. Right? So let's just try that. Let's go, let's say that's image 21 and image 22, right? They look pretty similar, right? So I think is it process image calculator. You can say, let's go image 22, and we'll subtract, and we'll make it 32-bit float result, and there you go. So this image minus this image gives us this. Okay? Let's blow it up, take a look at it. So it's pretty obvious the signal to noise, or the noise level as a function of position, changes a lot in this picture, right? And that's due to that surface coil phenomenon. As you move out here, the noise level gets really small. When you're in the middle, the noise level is quite high. So saying what the signal to noise of your picture is really depends on which part of your picture you're asking. And so this looks like where the heart is, right? Because we have slight differences due to the motion of the heart between those 2 frames, right? If let's bring in another one that's far away in time, say image 29. Bring that one in. Okay. Now let's look at image calculator. Subtract image 29. We get this difference image. Okay, so now the heart has moved a lot between those 2 frames, and we see a lot of differences, there. And this image has now been scaled. The maximum minimum scales it so that the noise looks like a smaller amount. However, we can probably still, even though there's a lot of crap here, a lot of signal that we don't want to include that in our noise estimate, there is a field right here where we can estimate and say, you know what, the noise level is probably about what it is here. Come out, do that. Let's do a, histogram. There's our histogram of pixel values out here. The mean should be 0, right? Because basically there isn't much out there that's moved, so it's just noise. So the mean, I hope, is 0 unless there's some other shift. Looks like about 0. See, the mean is 3, and the standard deviation is 54, right? So the mean is pretty well 0, standard deviation 54. So that's telling you that whatever pixel value you have, right, at a point in that image, if you took that image 100 times, right, and looked at that same pixel value, you would get whatever its mean value is plus or minus a Gaussian distribution with a standard deviation of 54. Right? That's what that means. And so when you're doing your signal to noise, you take the mean value, divide it by 54, and that's your signal to noise ratio. Right? Okay? So you're going to be asked to do some of this stuff on the problem set, but don't panic if you haven't used this software before or anything. We can have a tutorial time where we go through examples, or more examples if you need them. Okay? Any questions about that? All right, great. See you on Tuesday. And look, we hope tonight all the stuff will be up on the class website to download the problem set and instructions on how to download the software and where the data is.